Every single time you click a button online, you're kicking off this incredible, high-speed journey across the entire globe. It feels instantaneous, right? But the system design that makes it all possible, well, it's a true masterpiece of modern engineering. So let's trace that path.
Seriously, think about it. You click Buy Now, and just moments later, a confirmation pops up. But in that tiny fraction of a second, your request is already zipped across the planet, navigated a maze of servers, and triggered this whole cascade of complex operations. So what exactly is happening in that little gap? Let's find out.
Okay, so our journey begins the very instant your click becomes a little packet of data. And the first challenge? Just finding its destination on the vast, sprawling map of the internet.
Your computer actually has no idea where onlinestore.com is, but it knows who to ask. It sends a quick query to the DNS, which is basically the internet's giant phone book. The DNS looks up that friendly name you typed in and sends back a specific numerical IP address. That's the real address of the server we need to talk to.
Now that we have the address, we've got to send our request. And you can think of it like choosing a postal service. On one hand, you have TCP. That's like sending registered mail. It guarantees every single piece of your request arrives, and in perfect order. On the other hand, you've got UDP, which is more like a postcard. It's super fast, but a piece might get lost along the way. So for something critical like a purchase, you absolutely need TCP's reliability. But for a video call, where a dropped pixel isn't a disaster, UDP's speed is king.
All right, so our request made it across the internet, and it's arrived at the correct address. But here's the thing. It's not the only one. It's standing in a virtual line with millions of other requests, all knocking on the same digital door at the exact same time.
And this is our first major bottleneck. I mean, if every single one of those requests went to a single computer, even a really powerful one, it would just crash instantly. It just can't keep up with that kind of demand. It's a huge problem of scale and a massive single point of failure.
So the solution is this really elegant piece of technology, the load balancer. Just think of it as a digital traffic cop. It stands in front of a whole fleet of identical servers, and its only job is to direct the incoming traffic, one by one, to the next available server. This makes sure no single server gets overwhelmed.
And one of the simplest ways this works is a method called round robin. It's exactly what it sounds like. The first request goes to server A, the second one, server B, third goes to C, and the fourth, it just loops right back around to A. It's a super simple but incredibly effective way to spread the load evenly.
So, our request got routed to a healthy server. We're in, but now comes the next challenge. That server has to find and retrieve all the data you asked for, and it has to do it in milliseconds. The clock is ticking.
The secret to this incredible speed is a technique called caching, and this analogy is just perfect. Instead of running to the back pantry for flour and sugar every single time you need to bake, you just keep a little bit right there on the counter where it's easy to grab. Caching does the same thing for data, keeping the most frequently used information in a super fast, easy-to-reach spot.
And the process itself is what makes caching so powerful. When a request comes in, the server doesn't go digging in the main database right away. First, it checks the cache. If the data's there, bam, that's a cache hit and it's returned instantly. If it's not there, that's a cache miss. So the server has to do the slower work of querying the main database, but, and this is the really crucial part, it then saves that result in the cache. So the next time someone asks for that same piece of data, it'll be a lightning-fast cache hit.
Now, the language these servers use to understand and process our request is defined by an API, an application programming interface. It's kind of like a restaurant menu. It tells you, the user, exactly what you can order, like get product details or create a new order, and what information you need to provide. It's the contract that lets all these different parts of the system talk to each other smoothly.
We've mentioned the database a couple of times, but let's dive a little deeper here. This is the system's long-term memory. It's the massive, organized library where every single piece of information, every product, every user, every order is stored permanently.
And there are really two main ways to organize this library. You've got SQL databases, which are like these meticulously organized filing cabinets. Everything has a predefined structure, which makes them perfect for things like financial transactions, where consistency is absolutely critical. Then you have NoSQL databases. These are more like a flexible whiteboard, perfect for unstructured data, like social media posts, where you care more about speed and scaling out than you do about a rigid structure.
So what happens when that library gets too big? Well, you have to scale it. Vertical scaling, or scaling up, is like just buying a bigger, better filing cabinet. You upgrade that one server with more power. But you eventually hit a physical limit. You can't just buy an infinitely large server. Horizontal scaling, or scaling out, is like adding more filing cabinets. You distribute your data across many servers. It's more complex to manage, for sure, but it can scale almost infinitely.
Okay, so we've built a system that's fast, it's scalable, and it's organized. But what happens when things, well, break? Because they always do. Servers crash, networks fail. So the final critical piece of this whole puzzle is designing a system that expects failure and is built to withstand it.
This number right here, this is the gold standard that engineers are always striving for. It's called 5 nines of availability. It looks pretty impressive, but what does that actually mean in the real world?
It means the system is up and running for all but about 5 minutes and 15 seconds over the course of an entire year. For a major online store or a banking application, hitting this level of reliability is absolutely essential. It's non-negotiable.
But achieving that kind of reliability forces designers to make some very, very tough choices. And that's because of a fundamental law of distributed systems called the CAP theorem. It basically says you have 3 ideal goals: consistency, availability, and partition tolerance. And here's the catch. You can only ever guarantee 2 of those 3 at the same time.
This forces a critical trade-off. For example, a banking system is always going to choose consistency. It has to make sure that everyone sees the correct account balance, even if that means the system is unavailable for a moment. But then you take something like a social media feed. It prioritizes availability. It's much better to see a slightly out-of-date feed than to see no feed at all, right? So every system has to make a choice about which one of these it's willing to sacrifice.
This all brings us to the ultimate question in this whole field. After learning about all these components and the trade-offs and these strategies, what does the perfect one-size-fits-all system actually look like?
And the answer is, there isn't one. The real core philosophy of system design is that every single decision is a trade-off. The goal is never to build some mythical perfect system, is to deeply understand the specific problem you're trying to solve and then make the best possible choices to meet those needs. And that is the art and the science behind every single click.